We'll start by expressing the three unbalanced voltages as the sum of three components. The first corresponds to the positive sequence, the second to the negative sequence, and the third is the zero sequence. Now let's find a concise formulation for these equalities. We know that phase B of the positive sequence is identical to phase A, but lags by 2 pi over 3. We can then replace in the equations phase B. Similarly, phase C is the same as phase A, but leads by 2 pi over 3. We can then replace phase C in the equations. Next, for the negative sequence, phase B leads phase A by 2 pi over 3. We can do the replacement, and phase C lags by 2 pi over 3, and we can replace it in the equation. Finally, for the zero sequence, all three phases are equal in both magnitude and angle. We can replace phase B and phase C of the zero sequence in the equations. So, for each sequence, we only need one variable, giving us a total of 3 variables, which makes sense since we shouldn't need more than 3 independent variables to fully describe the original 3 unbalanced phase voltages. To further simplify the formulation, we introduce an operator A, representing a rotation of 2 pi over 3 in the complex plane, and substitute it into the equations. Now, observe what happens when we calculate A squared. We express the exponent as 6 minus 2, then apply exponential rules to write it as a product of two complex numbers. The first term represents a 2 pi rotation, which is equivalent to multiplying by 1. So we get A squared is exponential of j minus 2 pi over 3. This makes sense, since two counterclockwise rotations of 2 pi over 3 should be equivalent to a single clockwise rotation of 2 pi over 3. We can now express these relationships as a matrix multiplication. This is known as Fortescue transformation. It converts the 3 symmetrical components into the original 3-phase system. In practice, we often want to decompose an unbalanced system into its 3 symmetrical components to make analysis easier. To do that, we invert the matrix, giving us what is called the inverse Fortescue